G'day chemistry students. In this video we're looking at dot points 5.2.1 and 2 again, just in a little bit more detail. In the last video we were looking at Chatelier's principle, introducing some of the key concepts, and what we said was that one way that we could change an equilibrium system to make the concentrations of the chemicals in the system adjust, one of those ways was to change the concentration of some of our substances. So in this video, what we're going to be focusing on is explaining how and why those shifts that we looked at in the previous video actually work. Let's get into it. We can change the concentration of a substance that is in an equilibrium system, and what we would expect to see is a shift either in the forward or the reverse direction, left or right. And so we can increase or decrease the concentration of substances, and that can be done in a couple of different ways. So in particular, when we're reducing the concentration of a substance, that's usually because we're adding another reactant, and that reactant is not one of the things that's already in the system, so it wouldn't be A, B, C, or D in this example. And the whole idea of adding that reactant would be to consume one of the substances that is in the system. So for example, you could add a substance which will only react with B, and that will mean that it's consumed. And what we would expect to see is a left shift as a result. So when we look at B, if we're consuming it, we're reducing the concentration of B. That's going to decrease the reaction rate of the forward process. And that's going to mean that the reaction rate of the reverse process is going to be more dominant. Now, what that is going to mean is that there's going to be an increase in the concentration of AB in total, and a reduction in the concentration of CD in total as well. We can also make changes to some of these substances to increase the concentration, and that's simply just by introducing more of one of the chemicals that's present in the system. So for example, if I get D and I add more of D to that closed system, what we would expect to see is a left shift. There's going to be an increase in the rate of reaction in the reverse direction. So that left shift is going to mean that there is going to be an increase in the concentration of A and B and a reduction in the concentration of C and D. But let's now start thinking about how collision theory can be used to explain the shifts that we have been talking about when looking at Le Chatelier's principle. Again, I'm going to use my really common example, the equilibrium between nitrogen dioxide and dinitrogen tetroxide. In this example, what we're going to have is an addition of nitrogen dioxide to the system. When we do this, we increase the number of nitrogen dioxide particles. And from a collision theory perspective, what that means is there's going to be more particles, more reactant particles on the left-hand side. And that means there's going to be more collisions between those particles. If there's more collisions, more interactions, then that's going to increase the rate of the forward reaction. And if there's going to be an increase in the rate of forward reaction, then that's going to also mean that the reaction rates are no longer equal and balanced. The forward reaction rate is not the same as the reverse reaction rate, and that means that the system is no longer in equilibrium. If that's the case, then dinitrogen tetroxide will just get produced more and more and more, and its reaction rate will increase more and more and more. And as that additional nitrogen dioxide begins to become consumed, its reaction rate will decrease. And eventually those reaction rates will equalize. Again, at that point, we're back at equilibrium. A lot of the time, we like to visually represent that change as it happens, and we can graph the concentration changes of all of the substances that are in equilibrium against time. And so in this example, we're looking at the equilibrium between hydrogen and iodine gas forming hydrogen iodide, meaning that those two elements can form hydrogen iodide, and that hydrogen iodide can also break up back into its elemental components. Now in the example here, we see at the beginning a bunch of straight lines, no concentration change. That means that all three of these substances are in equilibrium in a closed system. What we see at this time period here, though, is that there is a drastic change in the iodine concentration. So in an instant, what we see is that the iodine concentration increases. Now that is probably because the iodine has additional iodine has been put into the chemical system. What happens then is that there's going to be a little bit of a shift. There's going to be a shift towards the right. There's more iodine particles capable of reacting, so the reaction rate of the forward process is going to be increased. And what we see is that the concentration of those reactants, the iodine and the hydrogen, slowly decline. And what we see is an upswing or an increase in the concentration of hydrogen iodide as a result, as more hydrogen iodide is being produced. Something else to note is that the rate at which the concentration of hydrogen iodide increases is larger than the rate of decrease of the hydrogen and the iodine itself. In fact, the hydrogen iodide has increased its concentration twice as much as the iodine and the hydrogen individually have decreased. And that's got to do with our molar ratios down the bottom. The hydrogen iodine and hydrogen iodide are in a 1:1:2 ratio. And so we see as the forward process progresses that we end up forming a lot more of that hydrogen iodide product in comparison to the amount of individual hydrogen and iodine that is consumed. Graphs like these in particular are an exam writer's dream, and that's because it's a really easy way to visually show your understanding of what's happening when a change happens in equilibrium. A lot of the time you might need to explain changes in equilibrium in writing, but you will also see that you may have to interpret or draw on a concentration graph like this. A lot of the time, what you'll get in questions like this is maybe showing all of the products in equilibrium, and then maybe you'll get told of a change that happened. So for example, you need to show that, iodine gas has been added to the system, and then you would need to then graph the curves afterwards to show how those concentrations change. So we'll look at a couple more examples like this in class, do a few practice questions, because as I said, these types of graphs are really useful for testing your knowledge in examination conditions. And so we'll look at those and see how we can apply our understanding of equilibrium and communicate our understanding in a graphical form. Thank you very much, everyone. In the next video, we're going to be looking at Le Chatelier's principle again in a very similar format, but this time what we're going to be doing is looking at how temperature can affect equilibrium as well. But until then, have a good one.